Okay, good day, everyone. So today we're going to end our discussion on ARIMA modeling. So make sure that the packages that we have been using are loaded already. And let's have a quick review of what we have discussed so far. Okay, we learned, class, that when we model a time series using ARIMA process, the data has to be stationary in mean and stationary in variance. If the data is not stationary in mean and stationary in variance, then we cannot use ARIMA. We will have to transform the data first by detrending it, making sure that the mean is constant across time, and perform some transformation so that the non-constant variance will be addressed. One of the most common way in order to address the non-constancy invariance is to get the log of the series. Okay, and one of the most popular way in order to address non-stationary in mean is to get the difference of the data. Okay, if there's a need to do both, okay, we first get the log, okay, and then after that we get the difference, not the other way around. Because getting the difference first and getting the log afterwards will generate some error numbers. Okay, so not a number or unspecified, undefined numbers. So we'll have to get the log and then get the difference. Now, doing so, getting the log and getting the difference is actually equivalent to what, class? We learned that that is equivalent to getting the, anyone please? Getting the, hello? Returns, be more specific. Thank you, Raul. Yes, thank you, Jerome. Yeah, it's getting the log returns. Okay, not simply the returns, because meron tayong discrete returns. No? We have discrete returns. So getting the log and then getting the difference of the data of the log series is equivalent to getting the log returns of the data. Okay, so quick review, class. We said that the ARMA stands for, AR stands for autoregressive, MA stands for moving average, and I stands for integration. Okay, we learned how to model an AR1 process. We said that an AR1 process makes use of past values of itself here in order to explain your time series. So y sub t or x sub t is equal to a certain constant alpha or delta plus phi sub 1 x sub t minus 1. So you're explaining your time series x sub t based on lagged 1 values of itself. So that this is an AR1 process with, of course, plus an error term or a residual. Okay, and then how about an AR2 process? We also learned that an AR2 process, on the other hand, makes use of lag. So in effect, you have your lagged 1 as your independent variable and also your lagged 2 as your independent variable in order to explain your data, which is x sub t. Okay. All right. So in general, an AR autoregressive lag or order P process uses the P lags of your time series in order to explain your time series itself. So you have your lag 1 x sub t minus 1, lag 2 x sub t minus 2, etc. up to lag p x sub t minus p. Multiply that by your coefficient phi sub p. Okay, all the phis here are your coefficients of your lagged variable. On the other hand, okay, I think I see a question. Okay, mamaya na attendance. On the other hand, class, your MA, moving average, models your data, your x sub t or y sub t or whatever time series data, based on past error terms, past residuals. So here you have a certain constant mu plus your residual at time t and your lagged one residual. Okay, if you recall, another way to write this is L of E sub t, right? Log of E sub t, this epsilon sub t minus 1. Okay, so we also learned about MA2. Okay, and then combination of your ARMA process, ARMA 1 is just order of 1 for your AR process and order of 1 for your MA process. So your equation looks like this. So any type of equation, class, I'm sure you'll be able to explain. All right. So what will how will we come up with an ARMA model, our ARMA model? Okay, we listed the steps before. First, make sure that our data is stationary. So there might be transformations needed for your data. And the amount of transformation is really dependent on what you're trying to model. Okay, if you're modeling the price itself, okay, so the best way to do it is if your price is not stationary, and usually prices are not stationary, except for certain, let's say, extraordinary prices, which are not affected by market forces. Usually, class, prices are either they go up, there's an uptrend, or there's a downtrend. Very rare for a price not to be perturbed or not to move in any onslaught of market forces. If that's the case, if there's no movement, if it's constant been all throughout over the years, then we maybe that price, that stock is I don't know what I haven't met a price that has remained unmoving, whatever the market forces, whatever the environment is. Usually, ordinarily, any price will be affected by whatever market forces it's happening. So there can be an uptrend or a downtrend. Okay, so bottom line is whatever the behavior of your stock price is, you have to convert it into a stationary time series. Okay, if you're just modeling the price, then maybe just getting the difference will be okay. If by getting the difference, you have already converted the data into a stationary time series, then that's okay. That already will suffice. If, however, you're modeling the returns, the log returns of that stock price, then you will have to get the log first and get the difference. Okay, I hope that's clear, class. So in your exam, for example, it depends on, sorry, let me check the message. What's this? Ishan, what's your message, please? I can't read your message.
No, sir, because I was getting an invalid link whenever I tried to log in sa Zoom. That's why I was
Okay.
late.
Sige, mamaya na lang later. All right.
Sige, sir.
So, okay, once you have converted your data into a stationary time series, then the next step, well, traditionally the next step was to construct your ACF and your PACF, because that will help you identify what type of model, ARMA or ARIMA model you're going to use. Okay, the PACF and the ACF are helpful tools in order to determine the autocorrelation of your data and what lags they are correlated. So as a guideline, we said that when if your partial autocorrelation has okay, let me ask you, class, for an AR process, how does the PACF look like? Anyone? For an AR process, how will your PACF, your partial autocorrelation function look like? Okay, you may unmute yourself, class. No? Okay, significant peaks. Okay, thank you, Jerome. Or it's a cut off. There are cut offs, right? There are significant autocorrelations in some lags. Okay, so cut off yun, no? Wala na sa iba. None in the others. So that's how your PACF look like if it's a, how about the ACF? How will it look like if it's an AR1, AR process? Anyone, please? Okay, it tails off. Okay, thank you. Tails off. So for an AR process, the ACF looks like there's a tail off. Okay. Now tail off is not the same as slow decay. Okay, I think I loosely used this before. I stand corrected. Tail off is not the same as slow decay. Ang slow decay class, you have autocorrelation across several time periods, and the autocorrelation tapers off very very slowly. Okay, unlike a tail off where there's autocorrelation in some aspects, but the tailing off is faster process as compared to a slow decay. All right. So for an MA process, it's the reverse. For an MA process, you look at your PACF. If there are significant cutoffs there, then and your PACF shows a tail off, then that indicates that it's an MA process. If it's an ARMA process, then it can be, sometimes it shows tail offs at both PACF and ACF, and sometimes significant spikes at both ACF and PACF. Okay, so they're both the same, they're both consistent. Okay, so after we have identified the AR and MA process, then we do the model. Okay, and then this will be a series of iterations. Then you try, how about, let's say, for example, you guessed that the model is AR1. After doing the model, after computing for the coefficient, and then computing for the AIC, then you do another one. You do an AR2, and then compare. So this is really an iterative process. So it's a long process, especially when you're doing this manually. Good thing now there are so many statistical packages. In our case, we're using R, so we can use the auto.arima function, which will automatically return to us the best model that we can use. Okay, all right. So then after that, what we do after we have generated the model, we will have to test. Okay, check the model, diagnose the model. We just don't stop at identifying the model. We will have to test for the residuals. Okay, testing for the residuals mean testing if the residuals are heteroscedastic. Sometimes you need to test if the residuals are normally distributed, but usually you test for the correlation, autocorrelation of the residuals. If the residuals still exhibit autocorrelation, then that might mean that your model is not the best. So you might do some more transformation. Okay, so that's one way. Or the next one is, if your model displays some volatility clustering, significant spikes at certain lags, okay, then that might mean that your ARIMA model might not be sufficient, because the ARIMA model will not be able to capture, okay, what we call volatility clustering. When we say volatility clustering, increase in returns tend to be followed by more increases, several increases, or decrease in returns tend to be followed by more decreases, decrease, 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 or increase, 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 increase. So that results into a plot where you have significant spikes, a clustering of spikes, okay, or a clustering of downturns. So when we have those, then ARIMA would not be the optional way to do that. And the good thing is that we can check if the residuals are heteroscedastic using the arch test, which we'll discuss in a while. So your exams class will cover both the data structures up to ARIMA, up to the testing of the model, up to concluding whether your model is okay because your residuals are already white noise, or concluding whether your data seems to show volatility clustering. Hence, the preferred model might be a GARCH model, which is generalized autoregressive conditional heteroscedasticity, which is supposed to be our next lesson. All right, so we have already, just quickly, we were using the BUD dataset. We use quant mode. Be sure to know how to use quant mode, class. Anyway, of course, if you're bringing your notes, then you'll be guided. Okay, but I suggest that you really familiarize yourself with your notes and also with the codes, because if it's, for example, the tendency of students, especially in open notes, is that they will not study. Okay, anyway, the notes are there, but sometimes that will take sometimes if you don't know where to look, then that can consume a lot of time. So oftentimes students who do not prepare, okay, tend to get lower marks, okay, because they don't know where to look, okay, etc. All right, so we already downloaded this. We already have the BUD data set. And what we did, class, was to create an object, adjusted BUD, which is just the adjusted price. Okay, and then I used BUD1. BUD1 is also adjusted price. This is from adjusted BUD. And we did last time, let me just show the plot of this. The plot of BUD1, okay, it tells us that the data is not stationary. Okay, quick review, class. What are statistical tests in order to determine if your data is stationary or not stationary? So you should be able to answer this quickly already, class. Okay, let me see some answers here. Okay, correct. You have the ADF and the KPSS test. So let's quickly test this just by way of review. ADF.test and then BUD1. Here okay, what's your null hypothesis here, class? What's your null hypothesis here? Anyone? What's the null hypothesis for the ADF test? Okay, unit root. There's a unit root. Therefore, there is a unit root. Let me just show this by way of review. AKA, what's this? Not stationary. Okay, loosely speaking. But technically, class, they're different. But oftentimes, they're just used interchangeably. Okay, and then the other one, let's just use both KPSS test of BUD1 also. This time, there's a difference in their null hypothesis. Okay, so just be aware of that. Here, there is no unit root, aka your data is stationary. Okay, they're testing different things. Okay, all right. So thank you, Abija. Thank you, and thank you for those who answered. You're correct. So if I run this, okay. So from the ADF test, the p-value is 0.72. Okay, so which means that this is greater than 0.05. Therefore, our conclusion is we fail to reject the null hypothesis that there is a unit root. So this indicates that BUD1 is not stationary. On the other hand, for KPSS test, take a look at your p-value. For our KPSS test, the p-value is 0.01. Okay, so we reject the null hypothesis that there is no unit root, class, right? It means that your data is not stationary. So in both tests, we were able to show that BUD1 is not stationary. Okay, so if we were just, okay, if you just wanted to model BUD1, okay, what should you do, class? So we're using this also as a quick review. What should you do? If you just want to model the prices, what could be the first thing that you should do, class? Hello? Any suggestion? I'm just modeling if I want to model the price? What transformation may be done first? Class? You can show it in the plot, right? From the plot, class. There, class. From the plot, class. Hello? Okay, we're talking about transformation, class. So since the data is not stationary, even as shown by the statistical test, context, we're modeling the prices, bad one prices. What do you think should be our first transformation? You may unmute yourself, class, so that we can we're a difference. Why difference, Vince? Also the same as Christine.
Easier, sir.
Easier, yes, of course, easier. And Christine, could you add on to that?
For me, sir, you stated earlier if we're only going to model prices lang po, then we only need to difference the prices.
If we're modeling the price, not necessarily, because what if the price also shows non-constancy invariance? Then you will have to get the log also. Okay, so take note of that, class. Here, it's not apparent that the time series has non-constant variance. Okay, it's not so obvious here. It's not apparent, but it's apparent that the time series has non-constant mean. Okay, all right. So since the time series seems to display non-constant mean and not necessarily non-constant variance, we're not sure about that. We can just first get the difference of your data. Okay, so let me create this object. Although we have created this before, dbud, which is just the difference of bud1. Okay, so when we plot this plot of dbud, let's see. Okay, so the reason why we're getting just the difference is because the data shows non-constant mean. Okay, we're not getting the log because it's not apparent that the data has non-constancy invariance. Okay, so and then since we are only interested in modeling the price, if we're modeling the log price, then definitely it's unavoidable for us to get the log and then get the difference because that pertains to your log returns. So if I run this class, okay, so now can we say that the data seems to be stationary already? Class, kindly chat yes, please. I said kindly chat yes. So the question, does the data seem to show stationary in mean? Answer, class. Okay, yes, thank you. So it's stationary in mean. So let's see. We can use the ADF dot test for dbud. Let's test if this is stationary. Oops, sorry. Wait. Sorry, I got the difference. No? Okay, then okay, let me just NA dot omit. Okay, so let me rerun this. Difference of bud1 NA dot omit is equal to true. Okay, so let me run this. Okay, just this one. I'm not anymore plotting it. Okay. Okay, so we have this. So we have a deed bud and then ADF.test. Oh, wait. What happened? Difference. Where's my error here, class? I already omitted the NA. Okay, where did I get wrong here? Because your debug will have a, because we're differentiating it, so it will have an NA. So we're omitting the NA, right? Let me see. If I run this again, did I run this properly? Control Enter, and then let me check the object difference bud. This one. Having difficulty with my mouse. Difference bud here. Okay, there. Oh, why is there still an NA? Ay, sorry, class. Apologies. Sorry. Where am I? Where's that? Should have recalled the number. Where are we? Here. Okay. This should work NA.omit. So, okay, NA.remove. Okay, I'm using the NA.remove. Okay, and then, you see, YOY. Okay, so let me just, I'm having problems here. Let me use this. Okay. It should work already. Okay. Okay. There. I don't know why that NA.RN did not work. Anyway, so I just specified from row 2 up to the number of rows of the bud. So if we do the, okay, so what do we have here? Okay, p-value is 0.01. So we reject the null hypothesis that the data has unit root or it's not stationary. So this confirms that our data is stationary. All right. And then let's, okay, let's compare class. If we don't get the difference, okay, of bud 1, okay, let's just create a model 0. So I'm skipping now the auto.arima. Okay, bud 1. Okay. So this class, I'm creating this model 0, where we're using Auto.ARIMA in order to model the BUD1 series itself. And let's see what happens. And let's print the result. All right. So what do you see here, class? So apparently the model for BUD1 is you just get the difference, right? Okay, you just get the difference. And what does this mean? You have no AR component, you have no MA component. Okay, I hope you're following, class. And let's compare that, class, with this one. Let's I'll call this mod 00, where I'm modeling this time Auto.ARIMA, and then I'm using the debud. Okay, what will happen, class? What do you think will happen with this one? You're modeling now the difference of the BUD series, the debud. What's the result, class? Okay, integrated component will be 0. And what's the AR process? What's the solution? What's the difference between that? Class? For BUD1, the suggested series is 010. Just difference it. Okay, that means, class, you have no model for this. You have no AR component, you have no MA component. You cannot use the past the past values of itself. You cannot use the past residuals, past error terms. Okay, so on the other hand, the second one, okay, so you have an ARIMA 00. Okay, now are they equivalent, class? Are these two equivalent? Are they equivalent? Kindly chat yes or no, please. Okay. Yes, Sir Ul, why? Why are they equivalent?
Sir, looking at the values, they're the same. If values lang po yung titignan.
Values of what?
AIC, BIC, sigma, log
Okay.
likelihood.
So based on that,
Opo.
okay. Okay. Tama naman yun. That's correct also. However, class, let's just do this intuitively. Okay, when we modeled BUD1, okay, what happened? The suggestion was to use an ARIMA 010. So there will be no AR component. You cannot use the past values of BUD1 to model BUD1 class, right? You cannot use its past residuals in order to model BUD1, the BUD1 time series. You just differentiate. When you differentiate, you generate a stationary data, okay? And when you forecast this, you just get the average. That will be the model. Kasi why are we doing a model? Why would we want to use BUD1 to model BUD1? Because we would want to forecast it. Okay. So if you have a model that's just ARIMA 1010, it means just differentiate. And then how do you now model BUD1? Just get the average. Okay, because you cannot use the past values of your BUD1 or the past residuals of bud 1 in order to model it. So that's what that means. And they're the same class. You know why? They're the same because here, what did we do here? You get the difference of bud, right? Am I clear, class? You got the difference of bud here. Am I correct, class? For D bud? Class? All right. I see only a few answering, class. How about the others? Isa lang nga lang, si Raul lang. Okay. All right. This is difference of bud, class, di ba? So when we model this, okay, what does ARIMA tell us? What does R tell us? Okay, that's it. You cannot create an ARIMA model out of this. 0 AR component, 0 MA component, and 0 differencing. Okay, no more differencing. No need to difference because this is already difference. But this one, class, the bad one, has not yet been difference, right? So if we difference this, if you're generating an ARIMA 010 model, it's just the same as ARIMA 000004 debug. Okay, notice they're both the same. No AR component, no MA component. The their difference is that in the integration. For bud, you have to use differencing of 1. For debug, you don't have to differentiate again because it's already difference. Okay, is that clear, class? So of course, you expect the same model because when you difference bud 1, you're also actually modeling debug, right? So I hope that's clear, class. No? Could you please chat if that's clear? I want to make sure that that's clear to you. Okay. About the others, class? All right, good. Now, okay, so if we take a look at debug, which is, so the model is, okay, the model is just ARIMA 000, right? If we check the ACF, so let's plot the ACF. Okay, wait. So we know, class, that names of mod 00, if I get what's inside this object mod 00. So this is actually a list of several objects. Okay, so you have here the coefficients. For example, if I want to get the coefficient, sorry, mod 00 $sign coefficient. So it will give us that the coefficient is 0. Okay, we can get the others. Okay, head, I just get the head, the first 6 values of mod $residuals. We can also get the residuals. So this is the residuals. Okay, sorry. What am I doing wrong here? Sorry, this is mod 00. My mistake. Mod 00 residuals. This is the head. It will give us the first 6 values. Okay. Now what am I doing? So after you model your time series, after you have generated your AR series, in this case it's ARMA 00, right? For debug, it's ARMA 00. So you cannot use the past values of itself. You cannot use the past residuals, error terms. So let's see, how will the ACF look like? ACF of mod 00 and then residuals. Let's see, class. Okay, so the ACF looks like, okay, this is autocorrelation with itself. It looks like white noise, right? There seem to be small significant, but it's maybe due to error in rounding off. So practically you have white noise here for your ACF. But what about the PACF? Let's see. So we're actually looking at doing diagnostics for our model. Residuals. Okay, PACF, the partial autocorrelation function. Okay, now we have a problem. Okay, because there seems to be there are significant spikes here. Okay, at later lags, no? For example, maybe at lag 21, 22, there are significant spikes here. There is autocorrelation function. There's autocorrelation present here. So this might indicate, class, that maybe the ARMA 00 might not be a good model, might not be a fit model for the BUD one. Okay, so let me just leave that as it is now. Okay, but we were able to see that based on the when you do diagnostics, your ACF and your PACF should show that there's only white noise. There are no significant autocorrelation among the lags of your data set. But here for the ACF, it's okay. But for the PACF here, you can see here significant spikes. Okay, let me pause for a while. Is that clear so far, class? Let me allow you to also. I hope you're following along. Okay, thank you. We're annotating actually what we have done in the past. Okay, so we're looking at the nitty-gritty details more so that you have a better appreciation of our data, of our process. Okay, so since that's BUD one or DBUD, so if we're processing BUD one, then this is the way to go. However, we can conclude that that based on the best AR model suggested by our software, it's not able to really capture the because let's plot the let's here. Okay, I haven't plotted. Let's plot the residuals, class. Plot mod $00 residuals. Where are our residuals? Letter R there. Let's plot this and see. Okay, you can see here some volatility clustering. Okay, that's why in our PACF you can see at some lags there are still significant spikes because it's not able to capture the volatility clustering. And this happens, class, as I said, during times of extraordinary times. For example, since our data started 2007, I'm not sure. This is 2007 global financial crisis. So during the global financial crisis, this is this one. Okay, but somewhere, BUD was not affected so much by the GFC, although you can see here a little bit of some spikes, but it's more here. Okay, and it's more here, also here, class, and also here. So these are more current events that happened to Bud Light. And as I mentioned in class, there was this issue of Dylan Mulvaney, who Bud Light tapped to be their let's say one of their sponsors, one of their advertisers, and there was a backlash, no, from their solid supporters. That's why the price of Bud Light really went down. And you can see here, this is more likely the backlash at this point. Okay. All right. But we're not, if we're interested in Bud, the price of Bud one, then this would be the way to go. Okay. However, if we're, was there a need to get the log, class, the log of this? No more. Since we're just interested in the price, and then getting the difference of the Bud price already show that it's stationary, then what was the use of getting the log? Okay, it would not matter, class. Okay, however, then let's go back to now to what we were doing. we said that we wanted to model the log returns of DL-BUD. So we had to create this object. Okay, we had first to get the log of BUD, quick review class, log of BUD, and then get the difference of log BUD. Okay, so this is now your difference log of BUD. Okay. So since I already have this data, I hope it's still with you, class. So this one, it should be part of your data, difference log BUD. Okay, and just making sure, since we're differencing here, I have to make sure that there's no empty value, NA value there. So the empty value, the NA value has already been removed. Okay, please chat if you have access already to your difference log data, because we're going to use that. We're going to use that again now. Okay. All right, let's wait for the others. Okay, good. So the others, I hope you have access already to that. So we're now modeling the difference of the log BUD. In other words, class, we're modeling the returns. Okay. We're modeling the returns. Okay, so let me go here to where we okay. All right. In the same manner, okay. So let me go to where okay. All right. So a while ago, this is what we were doing. Okay, we just reviewed, no? So we have the DL-BUD test. So let's first test if this is stationary. But we're quite sure that this would be stationary because a while ago the difference BUD was stationary, right? But let's just check. So using both the ADF and the KPSS test, control enter. Let's run this. Okay, and it tells us that difference log BUD is using the ADF test. Okay, we can see for the ADF test, the null hypothesis is that the data is not stationary. Okay, so the p-value here is 0.01, so we reject the null hypothesis. Okay, there's strong statistical reason to believe that your time series is stationary. Okay, for this one, KPSS test, it's the opposite of your null hypothesis for ADF. The null hypothesis here is the data is stationary. P-value is 0.08, so we fail to reject the null hypothesis. So on both counts, class, then your data is stationary. Okay, then we model this. Let's model, okay, difference log BUD, and then let's get the summary. We did this in the past already, but I'm just having a quick review. Let's model the difference log BUD series. And this is what the auto.arima. Okay, sorry, I forgot to put here trace is equal to true. Let's include the trace and then summarize this. All right. So this is the trace, and then it will generate several ARIMA models. And then it tells us that it generates this first with approximations. So the best model in this regard is 88084.61. That's ARIMA 004 with zero mean, with non-zero mean. Okay, sorry, it's with zero mean here. Negative 18086. This is lower. Okay, because it's negative. So that's with zero mean. So it tells us. Then after first finding the best model with approximations, it generated again another model, ARIMA 004 with zero mean, this time without approximations. 18086.02, 086.03, practically the same. The without approximations and with approximations. So the best model class is ARIMA 004, okay, with zero mean. Okay, and we learned how to show the equation for this class, right? So I will not discuss that anymore. So that's your MA1, MA2, MA3, and MA4. And we have here some measurement errors. This is your Ramsey root mean square error. Okay. This is your mean, the average error. This is your root mean square error. So what happens here is that you square the error first, then get the average, and then get the square root of that. Mean absolute error, mean percentage error, mean absolute percentage error, mean absolute standard error. So there are different ways to check your errors. Okay, maybe I'll ask some questions about what MAE is. So just for you to know, class, it's very easy, class. MAE, mean absolute deviation. So you have your residuals, just get the absolute value and then get the average. Okay, so it's very easy to even to compute all of this, very easy to understand. Okay, so okay, this is the same lang. So we have a model, it's ARMA 04, okay, ARMA 04 or ARIMA 004. No differencing because our data has already been differenced. Okay, so in our class a while ago, we compared, okay? So what's the difference between this one and what if, okay, what if we ask R to model log of bud? Okay, this one we already discussed a while ago, the modeling of bud one. Let's discuss this. Log of bud class, if we plot that, you can see that it's not stationary, okay? Just getting the log will not address the trend. It's not stationary. And then if we do the augmented Dickey-Fuller test, it tells us that, okay, we fail to reject the null hypothesis that there is a unit root, which means that the data is not stationary. So can we still do Autodot ARIMA for that? Yes. Okay, because R has the capacity to do the differencing. Okay, so if I create a model called Model 101, and then I'm asking R to generate an ARIMA model for log bud, trace is equal to true, and then summarize. So let's run this. Let's run the Autodot ARIMA for a data that's not stationary. Let's see what R does. Okay. What do you see, class? What's our final model? What's our final model, please? Class, can anyone unmute yourself? Class, how does this model compare with the other one, with the log bud data? Is there a difference, class? With our difference log bud data. This is the model for your log L bud, right? L bud ito. How does this compare with the model for DL bud? Low class? Waiting for your answer. Okay. All right, Vince, could you kindly explain your answer?
It's just like using the summary option, just like, it says like 014 for
Okay.
LBUT series, while for DLBUT it says 004.
Okay. So question, are the models, are the final models the same? When I say final model, the coefficient for MA1, MA2, MA3, MA4, are they practically the same class?
Yes, sir.
Yes. Okay. What's the difference between them? The difference is in the integration class. Okay. Take note, class, that LBUD is not stationary. So R had to perform some differencing in that. That's why you have here 014. For difference log BUD, why was there no integration needed? Why was there still 004? Why was this 004 class? Because class, hello, because waiting for an answer. Yeah, okay, Vince, thank you. Yeah, class, the data is already stationary, di ba? DL BUD is already stationary. Didn't we look at that, class? Didn't we plot DL BUD, difference of log BUD, right? So the model here is 004. The model for log BUD is 014. Okay, so for log BUD, if we get the difference, it actually becomes DL BUD also. So when you get the difference of the log BUD, it will be modeling the same thing. It's the difference of log BUD. Hence, we expect, of course, the same output. It will be ARIMA 004 for DL BUD and ARIMA 014 for log BUD. Okay. Is that clear, class? Kindly please chat. Kindly confirm if it's clear. Waiting for the others. Okay, any questions? I don't see the others keying in their comments. Okay. All right. Now, after we have generated our model, ARIMA 004 for your DL BUD or ARIMA 014 for your L BUD. Okay. Then, what do we do now? This is now the time we do diagnostics. We check our model. Okay. So let's do diagnostics for our ARMA 04 for DL BUD. Okay. So remember, this is just the same. ARIMA 004 is the same as our ARMA 04 because we're using the DL BUD data. Okay, so the model that we used is mod 1 for DL BUD. Okay, this one. We generated this model 1 for DL BUD. Okay, and then just like a while ago, we can get the elements, what's inside mod 1. Okay, and it includes the residuals there. And of course, you can get at the other items there. For example, mod 1 coefficients and mod 1 check. We have ARMA also, AR there. So what will this give us? ARMA. Okay. So 04, I'm not sure about this. ARMA 04. Okay, I haven't checked what ARMA indicates, but here you can see the order of your MA process. Maybe this is your differencing. So we can check what's inside the ARMA object. Let's see. In mod 1, here, you can access it. ARMA. Integer. So it's just the order. I wonder what one is. Could it be the difference? I'm not sure. We will have to check the literature about this. Okay, anyway, so let's okay, what do we do now, class? We check the residuals. Okay, we can create an object called resid, which is the residuals of your model 1, of your ARMA 04. Okay, so there are several ways to do this, class. You can plot mod 1 residuals or create an object called resid, which is just the residuals coming from model 1. So let's run this, and then let's plot this. Okay. What do you notice, class, about your residuals? Is your residual stationary? Comment, please. Yes or no? Yes. Okay. Stationary. Stationary in mean. Okay. You're correct. There are some volatility clusters here. Okay. So it means our model was not able to really capture this clustering of your volatility. Okay. Let's check ADF dot test of resid. Let's see if indeed statistically your model is stationary. 0.01, so we reject the null hypothesis that your data is not stationary. Okay, so stationary, our residuals are stationary. Okay, now, but we don't stop there, class. Let's check, for example, let's do the ACF of your resid, and also the PACF of our resid. Remember, this PACF and ACF function will give us an indication if there's an underlying AR or MA process. Okay, taking a look at our ACF. So just like the other one a while ago, okay, the bad one. This seems to indicate that this is white noise, the ACF function. Sorry, this is the partial autocorrelation function. You can see here significant spikes here. Okay, here. So this indicates that our model is not really able to capture some of the autocorrelation of your data, of your difference log data. For the ACF, except for some small spikes here, okay, it seems to look like white noise. Okay, but we have the problem with the PACF. Okay, so there are other tests that we can conduct. Okay, so we did this. So let me, okay, in the interest of time, I'll kindly copy this, class. Okay, let me just remove the results, copy this, and share it with you, and then kindly paste it in your RMD file, Control C. I'm going to put it in the chat box. Okay, oops, your message is too long. Okay, let me just, okay. So first is this, okay, Control C. Okay, let's first, and then this one. Let's see if this can Control C. Excuse me. Okay. So now that we have our model, what do we do? Well, we check the residuals, gather the residuals, check it. What we did here was to test whether your residuals are stationary. Okay, we also looked at the ACF and the PACF, and it looks like there are significant autocorrelations in different lags. So our ARIMA model should generate residuals that are white noise. Okay, there should be no significant autocorrelation. When there are significant autocorrelations among the lags, that means that your ARIMA model is not able to capture that autocorrelation. If that is so, then that could indicate that you should try to maybe transform your data, or maybe you should try to use another model. Okay, however, assuming that the auto.arima function gives us already the best model for your AR process, so no matter if we choose other models, you might be generating the same residuals. Okay, even worse. Okay, then that might necessitate to do another, to extend your model and do what we call a GARCH. So that's what we're going to do in the next lesson. It will be generalized autoregressive conditional heteroscedasticity. But in the meantime, let's test our residuals. So there are different tests that we can do. The Portman 2 tests allows us to have several tests, but they're actually related to each other. Okay, these are Portman 2 tests. When you say Portman 2 test, it means that your null hypothesis is clearly defined. Okay, so it's clearly defined. So we can name 3 tests: Leung box test, box test, and the Q test. Okay, but they're all related to each other. So let's start first with the Leung box test. So what does this test? Okay, it tests for the correlation among your residuals, autocorrelation. It checks for the absence of autocorrelation, which is what we want. We don't want your residuals to display autocorrelation. Okay, so the null hypothesis here is that there is no significant correlation at any of the lags. Now, where does this box test come from? It comes from the stocks package, but we don't actually need to load that class because it comes already pre-installed with RStudio. Okay, so there's no need for this actually. So let's create this test, Leung box test, and it uses this function box.test. Okay, so here we're modeling, the function is residuals of model 1. Of course, we can use recede or model 1 residuals. There are several ways to do this, but one is residuals function of model 1, and then let's just use lag is equal to 20. We're taking a look at the autocorrelation up to 20. You can use other lags here. Some use up to 36, some use just up to 12, or some use up to 16. No particular. Some use up to 24. No particular special case is concerned. And then you have to identify here type is equal to Leung box. So when we run this class quickly, when we run this, we see here that, okay, the null hypothesis is, recall, it's that there is no serial autocorrelation at any lag, no significant autocorrelation. But here the p-value is 0.04. So we reject the null hypothesis. There is significant autocorrelation at some lags. Okay, so which means that our ARIMA model was not able to capture that. Our ARIMA 004 model was not able to capture some of the autocorrelation. Okay, which is suggestive that our ARIMA model is not sufficient. Okay, We can also use the box. Okay, the second one is our okay. This one class. Box Pierce test. It's almost the same as the Leung box test. Magkaiba lang, there's just a difference in how it's computed. So same thing. Okay, let's use another one here. Let's use mod 1 residuals. Okay, same thing, class. Residuals of model 1 or model 1 residuals. So we're creating this object, the box Pierce test. And if we run this, same null hypothesis. Okay, the only difference is that in the p-value and in the test statistic, 32.601, here 32.197. So there's a difference in how it's computed, but the same result, practically the same p-value. So we reject the null hypothesis that there is no significant autocorrelation. There is. And then last one, there is also this Q statistic, but unfortunately, class, ito, same thing then, box.test. This has been deprecated already in stats package. So if we try to run this, I think it's only in 2021 that they stopped using this. Although there was before the Q statistics. So if you run this, okay, kasi ang argument only should be box Pierce or Leung box. So it's no longer existing. Then we can look for other ways to test that. Okay, for this one, okay, let me share this with you also. Control C. It's almost time. So I'm running out of time. Control V. So kindly copy that. And then based on the Leung box test for serial autocorrelation, okay, we were able to conclude that there is a serial autocorrelation among the residuals. And what does that indicate? It indicates that our ARIMA model is not sufficient. Okay, if you model using ARIMA and then you plotted the ACF and both are white noise, and you can check the Leung box test and the box Pierce test, and then it indicates that there is a failure to reject the null hypothesis that there's no serial autocorrelation. Okay, it means that there is no serial autocorrelation. Then that means that your ARIMA model is sufficient. Okay, is that clear, class? If our Leung box or our box Jenkins, no, this is box Jenkins, I'm sorry, box Pierce, sorry. Box Pierce test indicate that we fail to reject the null hypothesis, then there's no significant correlation autocorrelation at any logs, then that means that your ARIMA model is sufficient. Okay, your ARIMA model is sufficient. All right, since it's almost time, class. So lastly, the arch test. So to couple, class, your Box-Leung's test with your arch test. Okay, so what is this test all about? It tests your residuals if it's homoskedastic or heteroskedastic. Okay, homoskedastic means constant variance. Heteroskedastic means non-constant variance. All right, so we already did this. Okay, you can install the Nord's test library Nord's test, and then we can make use of the arch.test resid. Okay, so this is our residual, right, for model 1. If I run this, okay, it also makes use of the Box-Leung's test, but what's tested here is your residuals if they're heteroskedastic. All right, here it tells us that the p-value is practically 0, less than 0.05. And then the null hypothesis is that your residuals are homoskedastic. The alternative is that they are heteroskedastic. So what do we do here? We reject the null hypothesis that the residuals are homoskedastic. Okay, there's strong statistical reason to believe that they're heteroskedastic. So that tells us, class, that may heteroskedasticity tayo. Okay. All right. So this might indicate that the ARIMA model is not able to capture the our model class. Okay, so yung residuals, it displays heteroscedasticity. Therefore, assuming that that's already the best ARIMA model, then you'll have to go to another model. And it indicates to us that if we plot the residuals, di ba? There are what we call volatility clustering here, here. Okay, it's not the volatility, the residual squared tell us that, okay, there's clustering. Therefore, it means it might suggest that ARIMA might not be the best model for this, but it might be GARCH, generalized autoregressive conditional heteroscedasticity. Okay, so that ends our discussion class. That will be the coverage of our exams on Tuesday, up to determining if our ARIMA model is sufficient or not. Okay, so let me stop recording.